Great. My video is showing up, is it?
We're currently looking at the screen for Paul's talk.
Oh, yes, yeah, yeah.
Yeah, hi. You want me to say something so that
yeah, do you want to unshare your screen there, Paul? I don't think it'll show the video while I'm talking when we're sharing.
yeah, okay.
Yeah. Right, there I am. I see myself now. So I think we're all set to begin. So I'll start the recording and we'll begin. Oh, how long do you need to speak for, Paul? 45 minutes usually with some questions?
That sounds about right.
Fantastic. Yeah, that's usually great. 45 minutes talking, 15 minutes questions usually works very well.
Okay.
Okay, let's get the show on the road. Record. Well, good evening, ladies and gentlemen. Welcome to this monthly meeting of Astronomy Ireland for July. We have Dr. Paul Fellows from the Cambridge Astronomical Association with us this evening to give a talk about the Sun Sisters. That's our main event of the evening. And my name is David Moore. I'm the editor of our magazine, Astronomy Ireland magazine.
On your AirPods. Can you hear? Yeah. Can you hear?
Will you mute people, please, Laura, in the background?
Yep.
In fact, that's my first instruction. If anybody has their video on or their sound on, please turn it off until the question and answer session at the end. I'm the editor of the magazine, and I'm going to tell you a little bit about what the Society does, because we always have some new members, or non-members are very welcome as well. We'll keep that brief, gives up people who are having trouble getting into Zoom a chance to not miss the main speaker. So if you heard this before, there'll be a little bit of news, but we want to tell you a little bit about what Astronomy On does. The main thing is publish the magazine every month. It's the Irish Astronomy magazine. So if you're interested in space and you're in Ireland, you have to get Astronomy On magazine. Astronomy.ie is the website. Go there and sign up immediately after the talk if you don't already get it. If you do already get it, think of giving it a gift. Maybe there's a young person in your family or extended friends who's interested in space, and they might want to know what's going on in Irish astronomy in particular. Now, our format even therefore will be a little bit of past, our main speaker, and then some events that are happening in the future, some huge events coming up and lots to see in the sky, most of which is in the magazine. I'll tell you about that for about 5 minutes after our main speaker this evening. I want to welcome everyone from all around the 32 counties. I think we have a few people from abroad as well. And you're all very welcome. Everybody can come to these talks, not just members. Members get a discounted rate, of course. So what do? Well, we think we're the most popular astronomy society in the world. So that's relative to population. There are more members of Astronomy On, thousands of them around the country paid up. I've been running since 1990, over 30 years now. We have, as well as the monthly magazine, a weekly email that goes out to members to update them and remind them of some of the things that are coming out in the magazine. That goes out every Wednesday. There'll be one of those coming to you in the next 48 hours. There are these lectures every month, of course, which you can also get on DVD, and there are online recordings we can send you if you miss one live. They go back decades now with some fantastic speakers such as this evening, and people like the BBC's rock star astronomer, Professor Brian Cox, has given us talks, Astronomer Royals, loads more in between. Have a look on the website, you'll see the list. We'd like to get an expert in to tell us something about their aspect of astronomy aimed at the general public, which is exactly what Paul does all the time. So we're looking forward to his talk very much this evening. We also run various watches around the year, not too many during the summer because it doesn't get dark till too late. Couldn't really start till 11 o'clock in the evening if you want to see something faint in the night sky. We'll be kicking off the end of August with our huge event, and there'll be other watches during the year. We're famous for those. A Starbecue is that event at the end of August, the 31st, the biggest annual star party in Ireland. Giant telescopes in the Wicklow Mountains where the skies are extremely dark. You can see the Milky Way going down to the horizon with the naked eye. There'll be loads of telescopes there, professionally catered barbecue, talks, trade stands, fantastic evening. And we can guarantee you a clear sky, that if the night itself is cloudy, we'll actually rerun the telescopes the following Friday or Saturday until we get a clear sky. So you're guaranteed to look through extremely powerful telescopes, which most members of Astronomy Ireland don't even own telescopes this big. So that's our huge annual gathering for everybody in the country. People come from far and wide to see those, and they bring their big telescopes along as well if they have them. But you don't need to bring your telescope. We'll do all that for you. We do talks in schools as well, and we have a huge media presence. We've been doing that since the society began. We used to have our own monthly spot on RTE children's television, in fact, and we keep that up. In fact, since our last meeting, which was all about supernovae by Dr. Thomas Moore from Queen's University Belfast, who's actually part of a team that's discovered something extremely important about supernovae that enables us to figure out what kind of materials are going to produce in the universe. He'll explain it better. If you want to go back and look at the recording of the DVD, check that out on our website. You can order that. That was our July talk. Since then, our evening classes have begun. They're actually going on now every Tuesday. So hopefully everyone who's doing classes is signed in today. We always recommend them to watch the monthly talks as well. You can join them now and get the recordings of the talks you've missed. And you can repeat the classes live as well, free of charge, if you do so. Just because the class has begun, there's no reason not to sign up now. Details on astronomy.ie. Another thing we were doing, as I said, we had big media presence. We were back on television for Asteroid Day on June the 30th, telling people all about how we spoke to Brian May, the guitarist with Queen, who is actually an astrophysicist. I've met him and talked to him about, he did his PhD on his own merit. He didn't get an honorary degree. I'm sure lots of universities would like to have given him one of those, but he did all the maths himself. In fact, he was telling me how complicated the maths was, and he wasn't sure he did the right thing restarting his PhD after that Freddie Mercury fella convinced him to give up his astrophysics PhD and go into this band called Queen that you might have heard of. Anyway, great fun. Watch that. There's a recording of it on our YouTube channel. And if you go to our website, astronomy.ie, down the bottom, you'll see all of our social media, Facebook, Twitter, X, Instagram, and YouTube. And you can watch that recording. So it's about 8 minutes long. It's about Asteroid Day and a few other things happening as well. And that story about Brian May. So great fun if you want to watch that after the event. We've been having noctilucent clouds, these electric blue clouds that hang in the northern sky at this time of year from high latitudes like Ireland. I've seen a few displays myself. People have sent in pictures. They'll be in the next issue of the magazine. So keep an eye out for those every clear night. And if you want to hear me talking about them on radio, a member of the public spotted them in Donegal and was flabbergasted by them. You can hear that recording on our audio channel, which is astronomy.ie/audio. You'll see that recording there that we did the last couple of weeks. The International Space Station is returning to evening skies tonight. Now, we update this an hour or two before sunset every day with, is there going to be an aurora visible from Ireland? Quick heads up, sneak preview. No, we're not expecting one tonight, but who knows about tomorrow night and every day night for the rest of the year. And the International Space Station will be flying over at 11:38 p.m. A little bit low in the south. The passes will get higher over the next 2 weeks when we see it every night at a different time from tonight onwards. So watch out for that. It's a spectacular sight. It's actually been in morning skies up to this. I was watching it this morning around 3 or 4 o'clock in the morning. We issued a prediction yesterday. And there are 9 astronauts on board. Bit of a story there that 2 of them are stuck. They went up on the new Boeing spacecraft that's going to be servicing the International Space Station. Butch and Sonny are their names or nicknames, and they've been stuck. It's supposed to go up for 8 days. They've been up over a month now, and I don't think they have a date for when they're returning. Anyway, details of that will always be in our magazine. Brian Harvey writes a fantastic space station report every month for us. He's an internationally acclaimed author who's also Irish. So make sure you read his column every month and watch the space station, brightest thing in the sky when it flies over. So we'll post those details actually just after this talk, as long as it's before sunset, 10 p.m. We leave it to the last minute so we can give the very latest news, especially on auroras and things like that. Another thing's happening tonight, if you have to rush off early, it's 10 p.m. BBC 4, The Sky at Night, with which was originally set up by our old friend Sir Patrick Moore, and now taken over by his team Chris Lintoff and Maggie Adair Pocock. And they're going to be talking about the James Webb Space Telescope. If you miss it, it'll be repeated later in the week, and the exact date and time of that will be on our weekly members email that's going out. So loads happening as ever. Hopefully everyone's joined in now and we're ready to start the main event. I said, If you've got any questions, you can put them in the chat box at the bottom, or at the end of the talk, you can unmute your microphone and ask them out loud. We'll take them either way, but do save them till the end. Let our speaker get through his presentation that way. Our speaker is Dr. Paul Fellows. I said he's from the Cambridge Astronomical Association. His talks are aimed to appeal to people at all levels, from complete beginner to those who know where to start. And hopefully there's something in there for the more knowledgeable. I know it's a very interesting topic this evening that is changing as new information becomes available about stars moving around our galaxy. But Paul himself built his first telescope age 14 and experienced the wow of seeing the rings of Saturn for the first time. And I was looking at them at telescope at dawn myself this morning. They're almost edge on for the next few weeks. So if you've got a telescope, it's well worth getting up early to see Saturn right now. They're going to open up again till November, then they'll close down to be exactly edge on in March of next year. So Paul will know what that's like. He's been stargazing for 45 years, has his own private observatory where he images the sky, and he's chairman of the Cambridge Astronomical Association and presents public live observing evenings at the University of Cambridge to hundreds of people every week. So he's well used to talking to a lay audience, which is exactly what we want. He's also a frequent speaker at astronomy clubs in the UK and beyond, including being a regular speaker on board the Queen Mary 2 for the Cunard line. I feel a bit jealous of that, I must say. He holds a master's degree in natural sciences from the University of Cambridge and a postgraduate degree in computer science, also from Cambridge. And he's twice a winner of the Queen's Award for Technology. And he was recently presented the Lifetime Innovation Award by Emmanuel College in Cambridge. But tonight, he's going to talk about the Sun Sisters. It's a fascinating story I know a little bit about, and I'm looking forward to learning more. So over to you, Paul, and thank you very much for giving our August talk.
Well, thank you, David, for a wonderful introduction there. I'm just going to try and do the technical bit and reshare my screen. So you should first of all see a lovely picture of the background of my shot of the Milky Way there. I took that not in Ireland. I'd love to come and visit you guys for your festival. That sounds wonderful. I must make a point of doing that one year. But this was taken up in the Isle of Arran in Scotland. And get, like you say, the Milky Way going from horizon to horizon. But tonight we're here to talk about the story of the Sun's sister stars. And this was something that I was put onto by a question that somebody asked me once. They had heard that the sun clearly is alone in the sky, apart from its family of planets, and wondered if it was born alone or if it came into existence as part of a larger structure with a whole load of other stars in a star cluster or something. And I thought, oh, that's a really interesting topic. So I started researching away into it, and this talk is the eventual result of that. So let's begin at the beginning.
Paul, sorry, can I just stop you there? You're not sharing your screen, so we just see you at the moment.
What?
You're not sharing your screen, so we just see you at the moment.
Okay, let's try that all again then, shall we? Can you see the Milky Way?
Yep, it's coming up now.
Oh, okay. I assumed, as no one said no when I did that at the beginning, we were good. Now let's try the slides. Do you see that?
Yep, that's looking great.
Okay. Well, I've done the preamble, so we'll get going. And all good stories start at the beginning with where stars come from. And you quite often see this picture of Barnard 68, as it's known, quoted all over the internet as being a giant hole in space, which really gets me aggravated, and I start ranting about the fact that it's not a hole in space at all. It's a cold, dark, dusty nebula. And you can see there the blackness thins out towards the edges, and the stars behind are peeping through, showing really that this is a cloud of material in front of the background stars blocking our line of sight. When we look at this with an infrared telescope, we can see through the dust and the gas much more easily to the distant stars beyond and see what's going on inside. And what we find is a very, very cold cloud down around the sort of 30 degrees Kelvin, something like that, so just above absolute zero. And the material under gravity is gradually falling and collapsing inwards and getting more and more dense over time. And as it goes down in size, the gravity releases energy, just like you going down a hill on your bicycle, and so it will tend to warm the cloud up. And so the heat then tries to push the cloud outwards. So it's a very slow process, and it requires a long time for these clouds to collapse. But once they do, they sort of form into the next stage in the process. And I illustrate that with a picture of our old friend, the Orion Nebula here. If we looked back at Barnard 68 in about 5 million years' time, we would find that the gas and material had collapsed so much that the pressure and density right in the very center of the cloud would have got so extreme that young stars would have been formed in the middle by the collapse of the densest little knots of material. And when that happens, of course, the core of them can heat up to thousands, hundreds of thousands, even millions of degrees centigrade or Kelvin. And at 10 million degrees, the crucial point occurs where nuclear fusion can begin in the center of these young stars. So to begin with, a proto-star, as it's called, will glow by just from the heat of the release of gravitational energy as it collapses, but the core gets hotter and hotter until eventually nuclear fusion triggers, and suddenly the star output goes way high. And then what you see here in the Orion Nebula, if you kind of imagine this in 3 dimensions, what you're looking at is deep down into a large bubble of material, and the very bright overexposed center contains a number, 4 very large and some smaller, bright, hot young stars. And it's the energy of those stars from fusion pouring outwards that is now blowing that enormous bubble. You can see the blue edge to the bubble there, pushing that gas away. And so this is a self-limiting process. Once the first stars form in one of these collapsing clouds, they tend to radiate like crazy and blow away the remaining gas and stop more stars from being formed. So you tend to get all the stars born over a very short period of time. And that, of course, that's going to be crucial to our quest in looking for the sun's sister stars. So these nebulae collapse, some stars begin to form, and then the process is very rapid until it's switched off because the cloud dissipates. So this is the Orion Nebula, and the stars there are just a few million years old, burning furiously and blowing away the remaining gas and dust. If we looked back in another few tens of millions of years, we would find something more like this. This is the Rosette Nebula. It's just next door in the constellation of Monoceros, the unicorn. And it's a very big object. The core cluster that you can see right in the center, surrounded by the red rose-like sort of flower arrangement, giving it its name. The size of the full moon, as viewed from Earth, would fit inside that central region. So this is not an object to go looking at with a high-powered, highly magnifying telescope. This is one for binoculars, because you just can't get the whole thing in if you go searching for it. The cluster in the middle there consists of a number of bright white stars. There are sort of 2 lines of 3 maybe, and a whole lot of fainter ones in the center. But you can see that they've evacuated a bubble. They've blown this bubble in the center, and the surrounding ring that gives it that rose-like appearance, that is the hydrogen gas being blown away outwards by the radiation from these stars. You can even see some dark lines across it further out, where there is the remains of the Cold Dark Nebula, and a few stars perhaps still struggling to form in there. But eventually the whole nebula will be blown away outwards and just leave a young star cluster with none of that gas and dust there. And it's by studying these various nebulae in different stages that we sort of put together the stop motion view of the different stages through which stars get created. If we look forward to an object that's the next sort of in line, around about 70 million years after star formation began, the example of that is the Seven Sisters, or the Pleiades cluster. And here you've got the 6, 7, or 8 very bright, powerful young blue stars, bluey white, lighting up a whole load of gas. Now, confusingly, this gas is not from the original star forming process. The whole of the Pleiades cluster is moving around the galaxy in orbit, and has just ploughed through another gas cloud, and is the light from the brightest of the stars is lighting up the remains of that other gas cloud. So it's not actually part of the original birth nebula, but it sort of illustrates the point that gradually the young cluster emerges. Now, when you look, you can see the very small number of very bright stars in this, but the more you look, the more stars you see. And with the naked eye, it's 6, 7, or 8, hence the name Seven Sisters. With binoculars, you might see 40 or 50 stars. And as the aperture of your telescope that you look at it with increases, you might go up to several hundred. There are about 1,500 stars altogether in the Pleiades. And the deeper you look, the fainter the stars are, and the more they change color as well, indicating that they're burning with a lower surface temperature. So the brightest ones are these blue-white ones, and this all relates to their mass. And I've got a little chart that I've drawn up here, which shows the different colors and the associated size and the lifetime of stars, because big stars live fast and die young in astronomy. What we've got here is up the side, up the y-axis, if you like, the arrow pointing upwards is to increasing mass, increasing size, increasing temperature of the surface, and increasing burn rate. So at the bottom row is the little red dwarf stars, maybe 10% of the mass of our sun. Then we have the orange dwarfs, about half the mass of the sun. The yellowy stars, very similar to our sun, a little bit more massive. We have the yellow-white ones, then the white ones, then the bluey-white ones, and right at the top, the really massive stars that are the blue hot stars, with a surface temperature going from about 3,000 at the bottom for the red stars, 5,000 for the orange ones, 6,000 for the yellowy ones, up to about 20,000 up at the top of the chart here. But horizontally, we've got the lifetime, and it's one of those logarithmic graphs. So each column represents a 10-fold increase in time. And I'm representing the life, the length of time that a star will live. So the very top right, hottest, most massive blue stars there live maybe 1,000,000 years. And then they burn through their fuel ferociously quickly. Even though they are bigger and they have more fuel as a result of that greater mass, they manage to burn it so fast that after 1,000,000 years, they are over and done with, and they explode as a supernova. I've got a picture of the Crab Nebula there representing the end stage of a star as a supernova. Second row down, the blue-white ones, they live 10 times longer, so 10 million years, and again, end their life as a supernova when they run out of fuel. The white ones, it's 10 times longer again, so we're now talking, what, 100 million years? The yellowy white ones, they last 1 billion years, and then they're generally not massive enough to explode as a full-blown supernova. They will end their lives as a planetary nebula, and I've used the Eskimo Nebula there as a little example of a planetary nebula. It's where the star puffs off its outer layers in a much more gentle end stage rather than detonating as a huge explosion. Then we've got stars like the Sun with a lifetime of 10 billion years, so 10 times longer again. And again, the Sun will end in a planetary nebula. We're about halfway through the lifetime of the Sun, so we're, if you can see the mouse pointer, we're somewhere between the 4th and 5th yellow dot there on this chart. Which is, being logarithmic, represents half the lifetime, 4.5 billion years done, and then 4 or 5 billion years yet to go. For the two bottom rows, the orange dwarfs, they will live 100 billion years, 10 times longer than the Sun, and the red dwarfs probably 1 trillion years, absolutely enormous number. And both of those are such a long period of time that the universe is just not old enough yet for any of those smaller stars to have burnt out, no matter how far back in time they started. Even if they were shortly after the Big Bang, they've only had 13 billion years, and therefore they're happily carrying on for another, well, in the case of the orange one, another 90 billion years. They're only 10% through their fuel, and for the red dwarfs, they're only 1% through their fuel. It's quite amazing that none of these orange or red dwarfs have ever burnt out. We think they will end as planetary nebula, but we just don't know. Now, I explain all this in quite some detail because it's important when we start looking for stars like the Sun. We're going to be wanting to refer back to this chart. So we looked at the young star cluster in the case of the Pleiades that was about 70 million years old. That meant that, in fact, the first two rows of stars, the really big ones, had all burnt out already. They would have gone in 1 million and 10 million years, and so the only stars remaining in the Pleiades cluster are the white ones downwards. The others have already gone, and you can age a star cluster by looking to see what class of stars are still burning away in it. If you find the hottest, most vigorous star, that's almost like putting a date stamp on the cluster. Here's an older cluster than the Pleiades, and it's really just got white stars in it that are modest power. So this is perhaps 100 million years old at most, because all of the stars that would have been more massive with shorter lifetimes have now gone. Now, there are 1 or 2 stars that are glowing brightly and red in there, because those are the red giant stars, which are a stage that I missed out on my simplified diagram. So when the stars first start running out of fuel, they will change from being ordinary main sequence stars burning according to the color I showed. They all go red before detonating as supernovae or turning into planetary nebulae. But they don't spend very long in that red giant phase. It's quite a short part of any star's life. So just a few of them in that nice young cluster there. And what you can also see is that these clusters are more spread out when they're older. this one has got the stars spread over a larger volume of space than the Pleiades, and it's part of a natural process. When a cluster is born, all the stars are formed deep in the central, really dense region, and so they orbit around, held together by their mutual gravity, until eventually they will have a near miss with another one of their sister stars, and that usually results in one of them gaining a lot of speed and the other one losing it. And the one with the extra speed and momentum can quite often be thrown clear of the cluster. And so it's like a sort of boiling process. The stars that gain lots of energy boil away out of the cluster, and the cluster dissipates over time, and all the stars end up just orbiting round the main Milky Way, which I've just got a little photograph of a bit of the Milky Way here. You're probably much more familiar with it than I am. Here in Cambridge, we rarely see the Milky Way anymore due to all of the street lights from the city. Even the observatory has now been swallowed up by the expansion of the city. When I first came here, you used to have really good lights on your bicycle to find your way up the path to the observatory building. Not a problem anymore. But anyway, the stars get flung out of these young clusters, and they make their way just to become part of the general population of the Milky Way, all orbiting around the common center of mass. And our sun is no exception to that. We orbit round the Milky Way. We're going rather fast, 220 kilometers per second. It's a tremendous speed, 700 times the speed of a rifle bullet, in a giant orbit with a radius of 27,000 light years, roughly halfway from the center of the galaxy to the edge. And at that distance, we take 230 million years to go right round. That's a very, very long period of time. And in fact, if you look at the age of the sun, which I said is about 4,600 million years, you can work out that the sun is on its 20th lap of the Milky Way. 20 is a fairly small number. It amazes me really, but that's the number of times we've managed to complete one lap of the Milky Way since the sun was born, along with probably all of its sister stars in some distant star cluster that is no more and has boiled all of its stars away in that period of time. So the real problem about trying to find the stars that were born with the sun is where to look, because even just after 20 laps, trying to track back and work out where the original cluster might have been and where the stars that were the sisters of the sun could be is a bit like trying to unstir a cup of tea. If you can imagine pouring the milk into your tea or indeed your coffee and stirring with a spoon 20 times, that's enough to really create some chaos. And this slide says 16 times. The number should be 20, sorry. But the idea is really it'd be very, very difficult to try and run time backwards because the sun will have passed through the spiral arms and passed by other stars many times in that period and had its orbit perturbed. So rather difficult to go back and sort of unstir the galaxy and work out where we came from. So let's have a little look at that. So what should we look for? Should we look for nearby stars? That was my first inkling on this until I thought about the unstirring of the cup of tea problem and the fact that the stars might be wildly distributed by now. Should we look for ones that are on a similar path round the galaxy? Well, perhaps that's still true, even though their paths might have been perturbed a bit. They're probably not now in the galactic core or right out in the outer reaches, although some of them may be. But perhaps a stronger set of clues would be to look for stars with a similar composition, made of the same mix of elements. I mean, all stars are made mostly of hydrogen, about 75%, and about 25% helium, but the tiny remaining trace elements are a bit of a chemical signature, and it's likely that that reflects the overall mix of elements in the star cluster that the stars were born in. So looking at the chemical fingerprints a good idea. We might look for similar types of stars. And again, that goes back to my big stars live fast and die young. There's not much point in looking for really giant stars because they just will have died by now. What we really need to look at, though, is ones of similar ages. And of course, we can try and judge the age of a star. And if we can find ones that are exactly 4.6 billion years old, there's a good chance that they may have been born at least at the same time as the sun. And as I said, the process of star cluster formation in these nebulae is a very rapid process that switches itself off. So it creates all the stars within a few million years of each other. So that's probably our strongest clue. When we look out in the night sky, we see the plough illustrated in the picture on the right there, the Big Dipper, the saucepan, whatever you want to call it. And those stars, and in fact a group of 14 visible stars and about another 50 fainter ones, are in fact all sisters. This is called the Ursa Major co-moving group. These are young enough, only 300 million years, that they've only done one lap around the galaxy, and they're still moving more or less in the same trajectory. Their orbits are very similar, their age is similar, their speed and their composition are all about the same. And so we can see that this grouping were all born together. They're spread out over 30 light years now. That boiling off process has thrown them out into independent orbits around the galaxy. They're not bound to each other by gravity anymore, only by history and the fact that they all came from the same cluster. So the quest is not impossible. It's just that this is down to one lap of the galaxy, 300 million years. Our problem is that the sun and its sisters have probably gone round 20 times, and so we've got that unstirring the cup of tea problem. I said about the chemical mix. The Big Bang created just hydrogen and helium and a little tiny bit of lithium. 3/4 hydrogen, 1/4 helium. And so that's the composition of most stars. In fact, the older stars are almost pure hydrogen and helium. It's the younger a star is, the more recently it's been born, the more it tends to incorporate the heavy elements that were made in previous generations of massive stars that have cooked up elements from carbon through to iron during their lifetimes, and then blown up as supernovae, and the supernovae then make all the rest of the elements up from iron up to uranium, even plutonium and so forth, which then tend to be radioactive and decay away. But the heavy elements are all formed by previous generations of stars. So the universe is getting dirtier and dirtier, and younger stars tend to pick up more of these trace elements, or metals as astronomers tend to call them, including all of the things that are not hydrogen or helium in that category, which really annoys chemists because they know that carbon's not a metal. But it results in this chemical signature being quite a good clue as to the age. So if we sort of plot that on a graph, you can see here we've got a graph with the ratio of metals to hydrogen plotted up the left-hand side. where 0 towards the top there is the same ratio as the sun. And if they're more metal enriched, they go up towards the top of the graph. And if they're less metal enriched, if they're purer hydrogen, then they're towards the bottom. And you can see we've got 3 ages of stars marked out there. Young ones in blue, with the age range running across the bottom. Again, one of these logarithmic scales to try to get everything onto one chart. Intermediate age stars in green and old stars in red. So you can see the spread of the range of possible metal to hydrogen ratio is also changing, and it's not a very good indicator of the age of a star. If you just measure the metallicity, as it's called, say minus 0.5, it could be any age. So we actually need to find other ways of trying to do this. If it comes out at -2, then it's probably a very old star, because there are none of the blue or green stars on this chart that go down that far. So it depends what value you get as to which class of ages you can rule out. Now, back to this little picture again. The sun is indicated by the big blue arrow in that row where the yellow stars are, with the 10 billion year lifetime, and the fact that the sun is already halfway through that. Now that's important, because if we were to look even for the yellowy white stars in the row above, they will have all run out of fuel if they were born at the same time as the sun in 1 billion years. Only 4 disks there, and that represents a lifetime of 1 billion years. You have to be at least where the mouse pointer is here on the chart. This is where the sun is, and you can't be much more massive than the sun without already having run out of fuel. So we are looking at really only stars that are either like the sun in terms of mass and temperature and lifetime, or very slightly more massive. But anything that's further up the diagram on any of those top 4 rows, we can rule out immediately. Now that's a bit of a shame, because in fact the observationally bright stars are much easier to see, and the bright ones are all the ones in the top 4 rows. So we're doomed to looking for really quite faint stars in our quest, because they can only be a little tiny bit brighter than our sun, and even if they were just twice the mass of the sun, they would soon be running out of fuel around about now. There's some maths associated with this, which I'm not going to trouble you too much with, but there's a rule of thumb that works, which is that the lifetime of a star is, in years, 10 to the power 10 times the ratio of the mass of our sun to the mass of the star to the power 2.5, as it works out. So you can easily work out what the mass is, what the lifetime is for any given mass. And so it works out, if you run it backwards, that the upper limit for a star that could still exist, that was one of the sun's sisters that won't have burnt out by now, is just 136% of the mass of our sun. This symbol M with a little circle, that's the mass of the sun. So 1.36 times that is M, and if you plug M into this formula, you get 4.6 billion years. So anything more than 136% of the mass of our sun is dead and gone by now. So we're definitely looking for stars at the fainter yellow end of the spectrum. Now, the very common diagram for representing all of this is the Hertzsprung-Russell diagram. You probably, if you're an astronomer, you'll have seen this diagram many times, which plots brightness against color temperature. and the sun is marked there in the middle. And so at 1.36 solar masses, my little orange arrow points the way to the top end of the mass scale. So we're looking for stars that are where that is, down through the sun, down into the orange and red dwarfs. Those are the only ones that can still be around, that won't have blown up into a planetary nebula or a supernova by now. Okay, so let's just a word about the cluster. We're also looking for to see if we could perhaps identify the remains of the star cluster, maybe that's been blown apart. And often these star clusters are formed in giant structures. This is a very nice picture of Orion, with the Orion Nebula lower center there and the belt across the middle. But all of the rest of those glowing clouds of gas show that Orion Nebula is just one small dense region out of a much, much larger molecular cloud. So maybe we could at least identify roughly where we might have come from in that sort of scale factor of hundreds of light years in size. And again, we would use the chemical signature to do that, to try to track back. One of the features that you find, though, is that nature is much better at forming small stars than big ones. A very large complex of gas and dust will form tens of thousands of new stars and also be big enough to form giant stars, because the collapse will happen very rapidly due to the high mass, and so it can form a giant star and you need to do that quickly, because as soon as the stars light up, all the material gets blown away, as I said at the beginning of the talk. Smaller star clusters have lower mass, they collapse more slowly, they'll form very many fewer stars, and most of the stars will be very small, so very, very unlikely to form any large ones. And so we can kind of track that as well, looking for the chemical fingerprint, because it's those giant stars that will make all the heavy elements. The small stars only turn some of their hydrogen into helium. Medium stars can burn the helium to the next generation of elements, carbon, oxygen, neon, and so on. But it's only the giant stars which make all the elements up to iron and beyond, and when they die, throw out lots of metals. So if you see an expanding supernova containing lots of aluminium and silicon and magnesium, then perhaps that cluster was a very large cluster because it had many more of the heavy elements in it. Now, there's a clue from our point of view, because we pick up bits of the early solar system in the form of meteorites, and we can analyze these, and it shows that the environment out of which the sun was formed was very strongly radioactive and contained a lot of these medium mass elements, aluminium, iron, and so forth, often in their radioactive forms. And that suggests that the environment that the solar system formed in had some giant stars that had exploded nearby. So it seems likely that the sun was formed in a very large original nebula that was capable of building these very large stars that lived and exploded and created a very metal-rich environment out of which the sun can have formed. So that's a sort of very interesting argument, telling us that therefore the sun's probably got a very large number of sisters maybe in the tens of thousands. So it should give us some hope of picking some of them up. We might have had some giant sisters, but of course they will have died, blown up already. But definitely a large collection, a large nebula, and thousands of smaller ones out there for us to find. So if I move on now and just have a little bit of a look at the idea of whether or not we can see any nearby sun-like stars. They're nearby because they're easier to study, because we're looking for fairly faint stars. The sun is not a particularly powerful star at all. It's one of the more modest types, as I've said. And we can work out whether stars are nearby or not by measuring their distance. We can look to see if we sense any change in their position as the Earth orbits around the sun. It creates a situation where a nearby star, shown in the little purple in the diagram on the right, will change its position compared to the very distant background of the galaxy, based on the principle of sort of long thin triangle, with the base being the diameter of the Earth's orbit, 300 million kilometers, and maybe 3 light years, 3.26 light years away, this star will have an angle at the thin end of the triangle of 1 arc second, if you do the mathematics. We call that 1 parsec, 1 parallax second. And we can use this method to measure the distance to the nearby stars. And of course, knowing the distance to a star and seeing how bright it is, we can work out how powerful it is, and therefore know the mass, and also something about the age immediately, because of that relationship between the evolution of the stars and their ages and masses. So if we do this, we can plot some of the nearby stars, and what we find is that the nearest stars in the sky to us are the members of the Alpha Centauri system. There are 3 of them, Alpha Centauri A and B, and Proxima Centauri, the nearest of the lot, just shown there on the diagram, just beyond 4 light years away. A light year, the distance that a ray of light can travel in 1 year, is about 10 trillion kilometers. So these guys are about 40 trillion kilometers away, if you want to measure it that way. The next nearest star system is Barnard's star over here at about 6. And we've got some other faint objects just shown there. But we'll have a look at the nearby stars first. If we look at the Alpha Centauri system, it was originally recognized that it was probably nearby because it changed position from year to year, and very slightly relative to the background stars. And so Henderson measured the parallax of it back then in 1830s and found a figure of about 4 light years away, which shocked him, because that's really relatively close. The arrow's pointing out Alpha Centauri. It's in the southern part of the sky in the constellation Centaurus, so we can't actually see it from our observing in the north here. It was discovered to contain 2 stars, Alpha Centauri A and Alpha Centauri B, but we've since given them slightly better names. The brighter component is called Rigel Kentaurus, and we've given the name Toliman, which comes from a different culture and means the ostriches, to its slightly fainter orange companion, Alpha Centauri B. The 2 orbit round each other, captured by their own gravity. Takes 80 years for them to go round in a really quite elliptical orbit. So sometimes they're only 11 times the Earth-Sun distance, 11 astronomical units apart. Other times it goes up to 35, so quite elliptical. And the third member of the group was discovered much later, and that's the little red dwarf star Proxima Centauri. This orbits right round the outside of the two of them, really orbiting them as if they were one. It's so far away. It's 13,000 astronomical units away from the center of the group. So from its point of view, gravitationally, it's just really orbiting what appears to be a single object. Now, it's interesting from a sort of general astronomy point of view that we've already discovered that Proxima Centauri has some planets around it, and it's amazing that just next door, the sun's nearest neighbor should also have planets. So planets everywhere. And that's another story, though. We're really interested in the stars. Let's have a look at Alpha Centauri A, Rigel Kentauris. This is a star that is a G-type star, just like the sun, but it's a little bit more massive, 110%. That's within my maximum of 136%, but it does equate to a very slightly older age. When we age the star by looking to see how much of its internal processes have converted some of the elements over and the chemical signature of it, we can age Rigel Kentauris to 4.85 billion years. So it's 250 million years older than the sun. Close, but I don't think that's quite right, because that's a little bit too much of a difference for them to have been formed in the same cluster. The cluster formation process is quicker than that 250 million. So it seems initially that we might have hit the jackpot straight away, but we're not quite right. Now, just a word again, because the Rigel Kentauris is a little bit more massive, just 10% more mass, it burns its fuel 150% of the rate of the sun, and that will reduce its overall lifetime to 6.8 billion years. So it's nearing old age already. It's only got 1.8 billion years to go before it'll become a red giant and then dissipate as a planetary nebula, leaving behind the characteristic white dwarf that these small stars all tend to end up as. What about its companion, star B? Well, Toliman, as it's known, is an orange dwarf star. It's just a little bit less massive than the sun, 90%, but that means that it's burning its fuel at only half the rate, 50% of the solar output. We're not absolutely sure of its age. The likelihood is that it's the same age as its companion. They're very, very extraordinary if they weren't formed at the same time, but pure age estimates based on the composition of this give 5 to 6 billion years, which is not quite the same as the 4.85 that we measured for Alpha Centauri A. It shows how difficult this is, but I would imagine they're both about 5 billion years old. But this lower mass, 90%, and the 50% therefore burn rate gives Toliman an expected lifetime of 20 billion years. And so it's only a quarter of the way through its life, got another 15 billion years to run. Just shows how these slightly smaller stars are going to live a lot longer than stars even like the sun. And then we come to Proxima, then the nearest star to the sun, tiny little red dwarf, just 12% of the mass of the sun. And for the red dwarfs, because of the internal structure of them, we can date these much more precisely, and we do get 4.853 billion years. So that's compatible with the estimate for Alpha Centauri A and suggests that the whole cluster is probably of this age. But of course, a red dwarf star, they run on economy. It's only producing a 50,000th of the power output of our sun, very, very faint indeed. And that works out at a lifetime of 2 trillion years, probably to form a helium white dwarf eventually. But no star like this has ever actually reached the end of its life. So that's an extrapolation for its ultimate destiny. We've never been able to observe such a thing. Next nearest star, Barnard's star, another of these red dwarfs. This is also a very old star. We can see in the little animation its position in the sky changing. It's got very high proper motion across the sky. You can see a few years of the little dot moving against the background stars there. And that's what first attracted Barnard's attention, this high proper motion, leading to, again, a measurement of its distance and finding that it was the second nearest star to the sun. But this can't be one of the sun's sisters. It's way too old. It's somewhere between 8 and 12 billion years old. Of course, that's nothing for a red dwarf that's going to live trillions of years. What about some more sun-like stars out there then? And you may have heard of some of these because these are popular stars to turn up in science fiction stories and Star Trek and things. Epsilon Eridani, relatively nearby, 10.5 light years. And it's an orange dwarf star, a little cooler than the sun. So rather like Toliman. You've got the figures there, 82% of the mass, 73% of the radius. But only between 400 and 800 million years old. So this cannot be one of the sun's sisters. Way too young. And actually, I think way too young, really, for those science fiction stories talking about aliens living on planets around Epsilon Eridani. They're just, the star's just too young for evolution to have really got very far on any such planets. But we do know that there are planets there. We've discovered some gas giant planets in orbit round it, and we'll probably find there are smaller rocky ones as well as technology and observations improve. Another one popular in sci-fi is Tau Ceti, a little bit further away. And again, this is 80% the mass of the sun, so a little bit cooler and a little bit less power output. And this is estimated at 5.8 billion years. Well, that's a bit closer to the age of the sun, but it's still 25% too old. And again, some estimates of this suggest an even older age, but it is very, very difficult to pin these down exactly. One of the things that we note when we look at these stars is that the rotation rate of the star also depends on factors like the size. So this one is a little bit smaller than our sun and rotating in 34 days. Our sun takes just about a month to spin round, 26 days, I think it is. And that goes with being slightly larger. And so again, if you can measure the rotation speed of a star, looking at the Doppler shift caused by one side coming towards you as while the other side's going away, that gives you another clue as to what's going on. So we have to piece all of these different estimates and measurements together to try to get a handle on these things. Down in the constellation of Scorpio, though, we've got a better candidate, perhaps. 18 Scorpii looks like a star very, very similar to the sun. Just visible to the naked eye at magnitude 5.5 down there in Scorpius, 46 light years away, so relatively nearby, giving us a chance to make some good measurements of it. And if you look at the sort of physical characteristics, it's a mass of just 3% more than the sun, 1% greater radius, 4% greater power output. The surface temperature is just 42 degrees hotter than the sun. I think this is a pretty good match for being a solar twin, but not necessarily a twin in the sense of being born together. And the reason for that is it's too young. It's just 2.9 billion years old. So it's a very, very similar star to the sun. It's a solar analog, but it's in a much younger state. And that's quite useful to us because we can see perhaps it by studying 18 Scorpii, what the sun might have been like a few billion years ago. Of course, we have to allow for the fact the galaxy is getting dirtier all the time with all of the explosions of supernovae that have gone in the intervening billions of years, adding more of the heavy elements. So it's a little bit complicated. Now, if we looked at a timeline of our sun and 18 Scorpii, quite like this diagram, this is the 10 billion years or so of the life of our sun along this trajectory from the point where it formed in a cloud of gas, as we talked about at the beginning of the talk. Here's 18 Scorpii. It's about 2.9 billion years along the trajectory. The sun's ahead of it here at 4.6. And gradually, as it gets older, it will swell up. It's an exponential process. It will gradually get bigger and bigger and then run away to become a red giant towards the end of its life. And there's another star here, which goes by the catalogue number from the Hipparcos satellite of 102152, which we've discovered that is also a solar analog, but it's just beginning to enter its red giant phase. So again, studying these solar analog stars is quite a good way of piecing together the future history of the sun, if you like. I mentioned the fact that 18 Scorpii being younger has a different metal composition because of that gradual dirtying of the material that goes to form the stars. It's absolutely true. You can measure it, and we find that the younger stars have significant differences. They tend to be more turbulent as well, so it stirs the composition quite well. And we find that the 18 Scorpii has got 3 times more lithium in it than the sun ever had. So that's a bit of a signature. And there's a photograph of 18 Scorpii. There's no evidence of a dust disk around it, but we do think that we've discovered a planet in a 7-year-long orbit. So again, all of these stars are beginning to show that they have planets around them. So far, we've missed the target. We've found some stars that are like the sun, but they're either too old or too young or chemically different. Let's look at some that are actually better candidates. Here's one. Goes by the HD 186302 catalogue number. Just a little bit less massive than the sun, 95%. Very similar in temperature. Age 4.5 plus or minus 0.8 billion years. So this really could be born at the same time as the sun. A little bit lighter, it's going to live a bit longer, but it was born at the same time. And it's relatively nearby. I mean, we're now talking 184 light years away. So it's getting to be harder to study these objects at that distance. It was initially claimed that this was the first discovery of a true sister of the sun, but just in 2019, it's been suggested that the orbit around the galaxy doesn't match up very well. But that's not a massive problem because near collisions with other stars and so forth over the last 4.5 billion years could have deflected the path of these objects from each other. So that's not a particularly strong piece of negative evidence, but nevertheless, the 2019 paper suggested it didn't quite fit. The best candidate located up until this point in the story is this one, HD 162286. A little bit more massive than the Sun, 115%, but almost exactly the right age, 4.5 billion years old. A little bit more of the heavy metals in there, just 3% more, but I think that's not too far away from matching up. And we know that it's got a Mars-like planet in a Mars-like orbit. So 1.5 astronomical units from this star, there is a little Mars-like planet, just like we have. So very similar situation indeed. Very interesting. And there's actually a photograph of it up at the top there. It's indicated by the little blue line. So that chemical signature matters because early on the Sun's sisters would have been close by to us. And why are we interested in finding them? Well, if they were born together in the same nebula with the same mix of chemicals and then gradually scattered away from the cluster, they would have been very near to each other for many tens of millions of years, even 100 million years or so, before scattering away from the cluster. And whilst they were that close to each other, material from one star system could have made it from one to the other. And so it's possible even that the seeds of life on Earth as we know it might have been created in the clouds of gas and so forth out of which the stars formed. This is the so-called panspermia idea of the seeds of life being brewed up in outer space by chemistry occurring on the grains of soot and illuminated by the ultraviolet light from nearby stars, causing interesting chemical reactions on the nooks and crannies on these grains to form the complex organic molecules, and then those falling onto stars and planets around those stars and seeding the chemistry of life on any habitable worlds. And perhaps life on Earth originated in that manner. And if life on Earth originated in that manner, then its nearby sister stars would have also had the same material raining on their families of planets. And so if we can identify any stars that are absolutely the same age as the Sun with the same chemistry that seem to have come from the same original nebula, then those sister stars may have sister planets of the Earth, or at least cousins of the Earth, that may well have had the material of life raining down upon them. Or if not, then objects blasted off the surface, perhaps in a more extreme impact from planet Earth, may have been ejected from one solar system and fallen to the ground in another nearby system, whilst these stars were very close together. And so these are excellent candidates to go look for the signs of any terrestrial life. So that's my real interest here. I'm really interested in looking for Earth-like planets around other stars. I want them to be long-lived stars such that the evolutionary processes of life have had plenty of time to create complex structures, such as all the sort of animals and plants, and for there to be a chance even of alien civilizations. And I think the best places to go look are the stars that are the Sun's sisters. And so there is a point to this search other than just, wouldn't it be interesting to know that a certain star was born with the Sun? Actually, these are excellent places to go look for planets, and we're already beginning to do that, as you saw. So there may or may not be life on Mars, but there may be life on the planets of the Sun's sisters just out there waiting for us to discover. And with that, I'll bring the talk to a close, and I'll stop sharing the screen, and we'll see if anybody wants to ask me any terrifying questions.
Thank you very much indeed, Paul. A beautifully illustrated talk, very well explained, filled in a lot of gaps for me. I hadn't realized the idea of the panspermia till the end when you mentioned it, but brilliant, brilliant idea. If people have questions, they can type them into the chat box or just unmute your microphone and shout them out. There usually aren't too many voices competing. While people are typing away, I might just throw in a question of my own. The Hipparcos satellite mapping the movements of all the stars, that's not able to unfurl those 20 orbits we've made of the galaxy by any chance, is it?
I'm sorry, David, I missed the last part of the question.
Oh yeah, the Hipparcos satellite isn't able to undo the 20 stirs of the galaxy that we've had and figure out any of the stars that, you know, would have been the same place as the sun when it formed 4.5 billion years ago.
I don't think any measurement of where they are and where they're moving now is able to unstir the problem, because it's in the nature of maths. You may have heard of the three-body problem, which is an unsolvable mathematical problem. We can't even work out what the orbit of three objects around each other is going to be in the long term into the future, or indeed unwind it into the past. And we're not dealing with just three here, we're dealing with all the stars in the galaxy. So it's an utterly unsolvable mathematical problem to work out from where they are now, where they would have been more than a very short period back in time. Now, Hipparcos only measured things out to about 500 light years and increased our knowledge of the local patch of the galaxy, but 500 light years is nothing compared to the 100,000 light years that it is across the galaxy. So really, it didn't make very much difference. Gaia, that's up there now, is doing a better job. It's measuring the position in 3 dimensions and the speed of movement of 1 billion stars to much greater accuracy and giving us this fantastic resource. And it's through using that we're going to be able to pin down some more of the sun's sisters. There's work going on looking for sun-like stars and ones with an age of 4.5 billion years, but nothing on Earth, no mathematics that we've got is going to be able to unstir the cup of tea.
Well, we've got about 5 minutes for questions. Then we want to tell you how to save 50% on your Starbecue tickets and some of the amazing sites that are coming in the next couple of weeks. So do stay with us. I see Tom has typed in a question there. Can you read them yourself, Paul, or shall I read it out to you?
Hang on a second. Yeah, Tom, thank you for your question. It says, what is your own favourite candidate for being most like Earth? I think there are there's a catalogue of red dwarf stars called the Gliese catalogue, and Gliese 581 has a whole solar system that we know about. So planets B, C, D, E, F, and G. And 581G is very, very similar to the Earth. It's orbiting in the Goldilocks zone around this red dwarf star. I'm not saying the star is one of the sun's sisters, but if you're talking about Earth-like planets, it's a very, very good candidate. And in fact, there's a second candidate that's nearly as good in the same star system, Gliese 581d, which is in a Mars-like temperature orbit, but it's I'll explain that again. It's in an orbit that puts it at a natural temperature that's a bit colder than the Earth. It's a little bit further away from the heat source, so it would be a bit colder than the Earth, but it's bigger and has a big, thick atmosphere probably, which means that it'll probably have a very strong greenhouse effect and warm itself up, and again be a habitable zone planet. So there are some good ones out there. One of the planets that I'm very interested in, I discovered myself using the Kepler Space Telescope, and that goes by this extremely easy to remember name of KIC 9147029b, and it's again a habitable zone planet orbiting a sun-like star. So the star is 200 degrees C hotter than the sun. This planet goes around it. It takes 13 months to go around it. That puts it at a distance very slightly further away than the Earth is from the sun. And so even though the central fire is a bit hotter, it's absolutely the right temperature to be sort of a nice 20 degrees C or so. The only problem with it is it's about the size of Saturn, and is probably a gas giant as a result. So one of the other projects that I'm very much interested in, we're looking to see if some of these giant planets in habitable zone orbits around their parent stars have moons around them. And if you watched all the Star Wars series, you'll remember the forest moon of Endor, which was a Earth-like sized moon orbiting a giant planet at the right distance from its parent star. So that's what we're doing. We're looking for the forest moon of Endor out there to see if we can find any sort of Earth-like planet or indeed moon of a giant planet at the right sort of temperature.
Great, we're at 8:28. So if anybody has one more question, we might squeeze it in. And again, while they're typing that, I might just ask, what was do you know, is it known what the star formation rate was like when the sun was formed? Is it similar to today, or was it a lot more active back then?
That's a really good question, David. I don't know the answer. I think that we are just past the peak of star formation in our galaxy, is the fact I can remember about this. So star formation gradually got going, accelerated up and reached a peak, and we're now past it and on the way down. So maybe the star formation rate was more or less at its peak when the sun was formed, because it was the universe 13.7 billion years old. The galaxy is probably 12 billion years old, and the sun was formed after 8 billion years, so about 2/3 of the way through the history of the galaxy, the sun came into existence. The galaxy is now beginning to run out of gas and dust to form stars, and so it's beginning to slow down.
Great. Well, Mike Egan just passed a comment there. Thank you very much, and saying you've answered a lot of questions he had for a long time. Same here. I second that motion. We've come to the end of the Q&A session there, but I'm sure you're easy to contact online. People can find your contact details, Paul, if they want to ask you questions that pop up overnight in their sleep.
Thank you very much for your comments. I'm glad you enjoyed it. It's a pleasure to give the talk.
And indeed, thank you very much, Paul. Another excellent talk. I can't thank you enough for that. We're going to tell everyone now briefly what's in the sky, because it's all in the magazine. And then, of course, everyone wants to rush off and tune into BBC4 at 10 o'clock to watch the sky at night and hear all about the James Webb Space Telescope. So if you want to hang around, you're more than welcome. If you have other things to do, hopefully we'll see you again, maybe the future Starbecue, and maybe I'll come to one of your Cambridge events. They sound fascinating also.
Thank you.
Okay, ladies and gentlemen, I'll keep it brief. I have my notes here, so let's just go through them very quickly. As I said, a lot of it's in the magazine. So If you miss the details, we'll remind you to remember every week in the email, and you've got the magazine in writing as well. Planets on view, everything's happening in the morning sky. Saturn's the first up. Jupiter I could see this morning as well, and Mars and Jupiter are going to get close. So you're going to be viewing in twilight. That'll change by the time the barbecue happens at the end of August. We'll see Saturn through the telescopes. It's going to be one of the star performers. The International Space Station, don't forget, 11:30, 8 p.m. tonight, different time tomorrow night, and every night for 2 weeks until the 25th of July. In fact, in your magazine, you'll see tomorrow night, Regulus, the brightest star in Leo, is quite close to a lovely thin crescent moon. It might be very low down, but you might try and see that. But the similarly bright star Spica, the brightest star in Virgo, it's left of the moon this Saturday. Diagram in the magazine for that. And then Uranus and Mars get very close, about a moon diameter apart. And there's 2 nights to see that, as you'll see in the diagram in the magazine. That's on Monday and Tuesday next week, 15th, 16th of July. Now, you have to get up at dawn to see this, Mars in the morning sky. But all the details are in the magazine. I'd recommend setting your alarm for that. To see 2 planets in the same field of view of a telescope is extremely rare. Antares will get close to the moon next week in the magazine. Mars is near the Pleiades star cluster as well. So there's a lot happening for early risers in the coming month. We have the full book moon happening on the 21st of July. Full moons always get great attention for people taking pictures of them rising next to interesting objects. The summer full moons are always low down, which makes it even easier to do that. And then Saturn's going to get very close to the moon on the 24th of July. That's well worth looking at. And again, if you like getting up early, Pleiades star cluster will be near the moon itself. Mars near it first, then it's near the moon itself. And Mars won't be far away either, so that'll be a fantastic sight at the end of the month. And then Jupiter is reasonably close to the moon. It'll be easier to see than it was this morning, and I could see it easily with the naked eye. So at the end of July, it's going to be very easy to see. And having Jupiter, the brightest thing in the sky that you're going to see this time of year, and the moon side by side, that's going to be well worth setting the alarm clock for. We have a diagram for that in the magazine as well. And then looking into August, just to close, there's the Perseid meteor shower. Now it peaks on the same day as our next lecture, Monday, August the 12th. It's during daytime. So probably the night before, Sunday night, the 11th, and Monday night after our lecture. The lecture will finish before sunset, so you won't miss anything. They're the 2 nights to watch the Perseids. There will be a quarter moon in the sky, but it sets by 11 o'clock. And the best time to see meteors is always midnight onwards. So in fact, you will get a good view of it this year, especially if you can stay up late on those nights. Details of that will be in your August magazine and on the weekly emails. Don't forget to keep checking, follow us on social media for any aurora. We only get 2 days notice of those. Or any Starlink launches that are predicted, and the International Space Station predictions also. So that's all the news. Just a quick note of what's coming up before our next meeting. Our advanced classes are running now. You can join them, as I said earlier, details on astronomy.ie. If you want to sign up for our pure beginners classes, they're in October. You can enroll for those now as well on the website. And do get your tickets for the Starbecue before the end of this month, because the full price is €75, including all the food, talks, telescope viewing, everything all in. But it's reduced to €50 if you book early. That helps us plan numbers with our caterers. So you'll be paying 50% more if you leave it till after July 31st. There's a tip for you. Book your Starbecue tickets now if you haven't already done so. Full details, including the movie about Starbecue, are on the website. You can't miss that. Skype Nights on BBC 4, 10 p.m, as we said. And our next book, which I'll close with, is on Monday, August 12th, when we have Andy Briggs of Space Oddities in Spain. He runs a YouTube channel, thousands of followers. He's given talks to us before, brilliant speaker, always has fascinating stories to tell. And he's going to tell us about the incredible moons of the solar system. I think we're at it for over 200, 300 moons now. And some of them are amazing. 2 lectures ago, you may have seen the talk about just the moons of Jupiter. That was fascinating. So with 300 of them to cover, Andy Briggs' talk should be brilliant. I'd advise you to book your tickets for that. He's a superb speaker. So follow us on social media. Enjoy the space station. Do email us anything you see. We'll put you in the magazine. so your observation will be recorded for all time. If you want to join, the join link is on the top of the website. We're always looking for new members, especially beginners. You can give gift memberships if you're already a member. The more of us, the merrier. Keep us as the world's most popular astronomy society. You can go to our YouTube channel and have a laugh at me on the telly just over for Asteroid Day. Laura, Tom, anybody, if I've left anything else to speak up or forever hold your peace? No, that sounds good.